welcome to today's lecture. So today we will talk about shared memory and also memory mapped I/O using mmap. I will start directly with this short Menti up here. You should be able to see the code in the stream. So please log in there, and I will also open this on my phone now. And we will have a quiz today again. So if you enter your or add your team number or the number from the SLP test system, or if you use the nickname from the SLP test system, it will be easy to figure out who should get the bonus point. So let's see. We can directly click to the next slide, and this is a question. We can see people now signing up for the question. I will give you some more time to sign up for the question. And I only have one question at the beginning and one at the end, and this will determine who gets the bonus point. I think same as the last time we had a quiz, it will matter how fast you select the correct answer. So the fastest person getting both answers right will get the bonus points. Bonus point. Mm-hmm. Another note regarding Menti, if you don't remember it, please check the device for when the quiz starts, because the stream might be delayed, and then of course it's unfortunate if you miss the prompt and miss the question, because there's only that many seconds time to answer the question. Okay, let me just see whether there's still more movement, but this looks... Yeah, I think we've waited long enough. So whoever is still joining now has to hurry up and enter the quiz then. Okay, I'll start the quiz. Segmentation faults are something to be afraid of, are helpful for debugging, e.g. null pointer, in a child process also affect the parent process, or are dangerous for the system. And time is up. And very good. Most of you correctly chose the second answer, are helpful for debugging. They are definitely not something to be afraid of. We can work with segmentation faults. We had a ton of segmentation faults in really many thousand segmentation faults, many hundred segmentation faults per, probably something like around 100 segmentation faults per second or something like that. In a child process also affect the parent process. They don't affect the parent process. If you get a segmentation fault in a child process, this basically has no effect on the parent process. If you have a huge number of segmentation faults in a child process, then some operating systems might do something about it, but this takes a very, very long time. So you need a lot of segmentation faults before anything bad happens there. And in a normal case, they won't affect the parent process. are dangerous for the system? No, a segmentation fault is certainly not dangerous for the system. A segmentation fault is if the system goes in a completely normal situation and handles the request to access a certain memory location. And then the system decides, no, not for this memory address. This address, I'm not okay if this process uses this address. I will kill the process instead. And that's what we call a segmentation fault. So for the system, this is not dangerous at all. It's a super normal and secure situation for the system. Okay, let's continue. Let's maybe quickly have a look at the current leaderboard. Can we show this? Oh no, I can't show the leaderboard right now, but we will have the leaderboard in the end, and then you will know who is first and who gets the point. Okay, let's continue with this terminal window here. We start very similar as in the last lectures with our empty CPP file. I will call this now SLP7 CPP. We start with some main function, and there we have a return 0. Always a good idea to have that. We include, maybe I like the C standard IO variant. Okay, and then we can print F just so that we have something to start with. Hello world. Okay, so we now have a start here. We will compile this into SLP7. I don't care about the debugging capabilities, -G, don't care about them for now. And I will provide the source file and run this and just check whether our hello world program works. It works. So the next step is we wanted to do file IO. So I will create another file and I will call this file hello world txt. And here I will write some text in there. Hello world. This is a text file to, I don't know. Anyways, if you see this, apparently it worked. So let's try whether this works. So we want to read this file. We don't want to do this printf, or maybe we want to do a printf here. Maybe we want to printf a string and we want to read this into a string. So we want to read this in a buffer. So let's create a buffer. Okay, we need to create a buffer with some size. This is not a good idea because if you now read into this buffer, you cannot know whether you have a buffer that is large enough to read into this buffer. So maybe let's, before we do that, check out what the options here are. Let's maybe check out what getS, for instance, would do. getS is, yeah, maybe not so clever. Look already at the first line here. It says deprecated. getS is not a good idea. Description: never use this function. The description already says this. Okay, so maybe we should not use this function. Let's try fgetS. fgetS. Okay, that's a bit better because here we can provide a size, and that's important. If we can provide a size, we know that we don't read too much. I mean, let's try what happens. I want to try what happens if we use getS. getS is unfortunate anyway because we only can read from standard IO there. So let's try what happens if we do that. Okay, let's compile this. getS was not declared. Yes, we need to check out how to use this. It's standard. It is standard IO, but maybe. Man getS. Char pointer getS. Here. LSB deprecates get_s, marks get_s as obsolescent. Okay, so this is removed from C11. So what we need to do is we need to compile this with an older standard, then we can still use it. So I'm showing this to you because I think you should see what happens if you try this. But you should, of course, never use this in practice. What is the standard here? GNU++? 98. Okay, this works. Is deprecated? Yes. Which it really does not want me to use this function here. You can see this. It's deprecated and is. Can you? Maybe this is a bit truncated, so I will just scroll this up. You can also always say in a chat if something is not visible. If you feel like there's something missing, then you can always tell me. Yeah, the window is a lot larger, so you were not able to see. Now it's much better, but probably it's not readable anymore because the font size is so small now. Let me maybe zoom in a bit. Yeah, this is a lot better, but at the same time, the line is not even long enough to compile. Okay, so maybe we choose the font size one point smaller. Yeah, this should still work. Okay. So what we see here is still not all visible. Let me just move this a bit up. Yeah, now it works. What we see here is that the compiler really does not like this. The compiler says it's deprecated, it's dangerous, should not be used. Let's use this. Let's try what happens. We run this, okay, and now I will just provide more input. Remember that we only had 1 byte of space, and I write a lot of A's now here. Okay, so this immediately corrupted the stack of my thread. This is really not very useful because the software cannot really prevent that this happens because the software does not know how much data will arrive here. So instead, let's use fget_s. That is supposed to be more secure. So let's check out what fget_s does. Fget_s also takes a character pointer, returns a character pointer. It takes a size, it takes a file pointer stream. Okay, so let's see how this works. The other option that we also can use, if we don't want to use fget_s, we can also use fread. Maybe we want to use fread later on. Fget_s, at most 1 less than size characters from stream, and it terminates them with a null pointer. Very nice. So let's try to use this. We provide a size here. That means we only have 4096 bytes of space here. Of course, if we would write this in a more clever way, we could malloc this buffer, and with other f file functions, we could search first with, for instance, with lseek, check out how large the file is, and then allocate the right number of bytes. But we are not very much interested in this part today. We want to figure out how memory mapped files work. So we want to provide a file stream here. So we need to use fopen to create a file stream. File pointer f equals fopen something. Okay, we need to figure out how fopen works. Fopen. Okay, this takes path name and mode. The function fopen opens the file whose name is the string pointed to by path name. Okay, that makes sense. And the mode, the argument mode, points to a string containing string beginning with one of the following sequences. Okay, so this would be, we want to open it for reading. I don't care too much about writing, so we will just open it for reading. R+, completely fine. Okay. R or R+. Then we can also write if we want to. So let's do this. And oh no, this is not here. This is not F. We have to provide that here, R+. And here the name, so this would be, we want to open hello world txt. And then we want to pass the file pointer here, fgetS. Let's try whether this works. C++. Now we don't need this weird standard setting anymore, so we can work with the current standard. Hello world. Okay, so this does not really work. Take a look at this. So this is working. The other part is not working. Why is it not working? Let's check out fgetS. fgetS. A reading stops after an EOF or new line. Oh, this is not very nice. So this function cannot be used for our use case. It's not very helpful. It can be very helpful if you want to read line by line, but in our case, we can't use fgetS. We will use fread instead. fread, and oh, fread, we again have to check how fread works because we don't remember that. So it takes a pointer where it should write to, size, and then mmap, number of members, number of items of data, and each item should be size bytes. So we provide 1 here for the character, and then the number of bytes that we want to read. And here the file stream, and here we provide the pointer, and it will return how many bytes were read. Okay, and this is all information that we get from the man page. So this is really convenient. So we can provide 1 here, or the alternative, if you want to be super precise in the way you program, this can be even better, although we don't expect some of these to change. But of course, this can lead to difficult situations. For instance, if you have a program where you have wide characters, if you have UTF-8 characters, there can be corner cases that can be quite tricky. So you have to be a bit careful there in the general case, at least if you write production quality software. For academic software, there's a bit more tolerance, of course. So let's compile this again, and we run this. Okay, this seems to work. Where is this P coming from? Okay, this is a bit weird. There's a P coming from somewhere. So did I add this in my program? No, definitely not. So let's see where this P is coming from. Interesting. I think I know where this is coming from. Let me try the following. I will place a character here, and I will call this character test, and I will make it equal to D. Let's try whether this changes this output. No, it doesn't. Interesting. So my suspicion is that fread doesn't null terminate, and therefore this reads whatever follows. Oh yeah, in the other direction maybe. Let's try this. Whatever follows this array, or whatever was in this array before. We can also try this. We can try and fill this array, size t, I equals 0, I smaller than 4096 plus I, and then buffer at location I equals E, just to try whether we can change what this value is. Oh yeah, oh, okay, this is just running until the next 0 byte, and this is probably a pointer or something that has a 0 byte somewhere, or maybe not a pointer but some uninitialized or maybe some unused space on the stack. So this is clearly not nice, because we need to terminate this with a null byte. So what we can do is we can check out how many bytes were read, and then null terminate this buffer. Buffer at offset bytes read. Let's think about how this works. fread, if we read 0 bytes, then bytes read would be 0, and we would set offset 0 to 0. Makes sense. If it's 1, this would be 1, so we set offset 1 to 0. Okay, makes sense. By the way, does it make a difference whether we write this or this? No, it doesn't make a difference. We write a 0 byte there in either case. So let's run this. Okay, now it works as expected. We are seeing the file here. The file content is printed, but this is file IO from C, and there's also POSIX equivalents of these functions. Let's use the POSIX equivalents as a start. So we don't use fopen and fread anymore, but just open and read. Let's check out how they work. Man read. This is the wrong man page. There are multiple man pages for read because there are multiple read commands. For instance, there is the read command on the command line, but we want to see the programmer's manual, so we will check out manual number 3 for read. Here you can see this manual page is part of the POSIX programmer's manual. Read from a file unistandard H. Okay. And then we have the read function here. It returns a size t. This is a signed size t. File descriptor, buffer, and number of bytes. So it's quite similar as the other variant, but we have to include another header. We have to provide not a file pointer, but a file descriptor. And this has to be provided as the first element, and then the pointer, and then the number of bytes we want to read. Let's try this again. This works. So file descriptor, buffer, and then the number of bytes. Okay, let's go for the next function, because now we need to provide a file descriptor, and for this we need to check out open, man3 open. Okay, so here we need these two headers, and open takes a path and open flags and then further arguments. These dots, you might know these from printf. Printf also has these dots because you can pass an arbitrary number of arguments. Let's check out which flags we can provide here. Okay, do we want to open the file for execute only, read write, open a directory for search only, write only, append, create, if we want to create the file, so we can specify all the different modes that we need. Okay, a lot of options here. I think what we want to have here is we only want to open it for reading, so we can choose read only or read write if we decide to write to it at some point. Yeah, let's use read write, because why not? And this is just the flag that we provide here, open, read write. And this, as you've seen, this returns a file descriptor. A file descriptor is nothing more but a number. And this file pointer that we had before, this is a pointer to a dynamically allocated struct. And this struct would contain the file descriptor. So in the end, you will still use the file descriptor internally. Is there any benefit in using the POSIX functions instead of the C ones? It depends. There are systems where you can gain a minimal performance advantage out of this, but this is really negligible in most cases. One advantage is maybe if you want to write, there's not much of an advantage. Maybe file descriptors are smaller. There's one advantage, of course, that I will get to in a second, because file descriptors are more compatible with other features of the POSIX standard that we want to use in a second. Okay, let's try whether this still works. We just replaced this by POSIX functions, and I hope that this still works. Oh, it doesn't. Oh, read write was not declared. Oh, I forgot the headers. Let's just copy them here. So we need to check out what the headers were stat and cmtl, file control. Okay, stat and file control. Let's compile this. It works. So the compiling works. Let's see whether it executes, and it still works the same way. This is still super inconvenient because I still need to determine like how much do I read. I need to issue these read commands. I need to create a buffer for that. This is still very, very inconvenient. And for that, we will use a different function now that makes this all more convenient, and that's mmap. Let's check out mmap. Mmap takes a lot of arguments. Okay, so let's go through these arguments. Void pointer address. Okay, let's check what address is. So let's first check what mmap does. Creates a new mapping in the virtual address space of the calling process. Okay, so this creates some memory mapping. The starting address for the new mapping is specified in address. Okay, so we can specify an address here where our buffer should be placed. The length argument specifies the length of the mapping, and it must be greater than 0. Okay, makes sense as well. If address is null, the kernel chooses the page-aligned address at which to create the mapping. This is the most portable method of creating a new mapping. So we should provide null if we want to write code in a portable way. If address is not null, then the kernel takes it as a hint about where to place the mapping. On Linux, the kernel will pick a nearby page boundary, but always above or equal to the value specified by mmap min address. This is an important part here. This is a hint. The operating system is free to ignore this. So if the operating system is free to ignore it, then maybe we also don't want to use this. What use would it be to use this? Sorry, I need to go back to the main page and copy this over. What use would it be to use this hint, to provide a hint, if the operating system ignores it anyway? So let's just provide null. We also don't care about the actual address. And we will create character pointer buffer equals mmap. We provide null here. Doesn't matter whether we specify null or null, it does not really matter. The one can be better in terms of making sure that the type is correct, but in this case I think the 0 visualizes very well that this is really just a 0 value that we pass here. The length, we need to provide a length, but we don't really care about the length now. So let's start with 4096, and then later I will show you some interesting parts here. Okay, so let's try this. So I have this buffer here. I still want to null terminate. Do I need to null terminate anything? Maybe I don't. Let's see. Offset. Let's check out the man page again, what this offset does, but I think I know what this offset does. Let's scroll down. There's a lot of arguments here. We can also with slash search for offset. The offset argument should be, wait a second. Let's start at the beginning. Offset. Okay. This is only a specific case. No, this is not. The contents of a file mapping are initialized using length bytes starting at offset in the file. Okay, so we want offset to be null, 0. File descriptor fd. Let's check out whether this is the file to open. Yeah, in the file or other object referred to by the file descriptor fd. Okay, so fd and offset are clear now. Length is clear. Prot and flags are not clear yet. Let's check out what prot and flags are. The prot argument describes where the desired memory protection, of the mapping. Okay, so I misread the sentence. The prot argument describes the desired memory protection of the mapping. So we can specify one of these flags here: prot exec, prot read, prot write, or prot none. So we want to provide maybe prod read. We want to read the file. We maybe want to write it, but we didn't really decide this yet. Yeah, we can see. And then we have the flags argument. This was the second one that we still needed to figure out. So this is prod read, prod write that we need to remember. And the second one is here, the flags argument determines whether updates to the mapping are visible to other processes. Okay, this is already an interesting hint. Other processes mapping the same region. This sounds very much like shared memory. Map shared, share this mapping. Okay, interesting. What other options are there? Map private, create a private copy on write mapping. Okay, so we want to start with a private mapping. So for the flags, we provide map private, and here we provide prod read or prod write. So now it's readable and writable. The file descriptor we provide FD, we call it FD, and the offset, we don't care about the offset. We want to read the file from the start, so it should be 0. We don't use any offset in the file now. So we open this, we do this. Let's try whether this already works. This would be a one-liner that replaces all this complicated file IO. Let's see whether this works. Oh, maybe not a one-liner, because if we want to make everything very beautiful, we should unmap. This is not necessary in this specific case, but it can be necessary in other cases, especially if you really share memory. Then unmapping can be important, so that you don't leak memory over time. So, oh yeah, this void pointer to character pointer, I need to cast this to a character pointer. Then we can see, compile this, we run this. Whoa, this is really, really nice. So I will not use ever this again. No more C file IO. I will only use mmap from now on, because this is so much more convenient. Now the file is just in the memory. Perfect. No matter what size it is. So maybe this is the next step. So let's check how large mmap, how large the mappings can be that mmap creates. So this is 4 times 1024, right? Let's try something like 1024, and I will already provide ULL for unsigned long here. So let's try 1024 times 1024. So this is 2 to the 20, right? 2 to the 10 times 2 to the 10 is 2 to the 20. That's 1 megabyte. And we, of course, should unmap the same size. Okay, so maybe we should make a constant for that. We call this buffer size. And now we delete this here and create a constant up here, define buffer size. I didn't understand why this is better than fopen fread, except shorter. So one advantage of mmap is that you don't have separate read calls for reading the data block by block, but instead you leave all of this work to the operating system, and the operating system can handle this in a more efficient way. It's less code. Writing less code is always better, I would argue. Other than that, if you work with really, really small files and only for a very short amount of time, like not frequently reading from it, not frequently writing to it, then fread or fwrite or read or write could be more appropriate. But in general, I only use mmap. If I work with file IO, I haven't used fread or read in code that I write for many years, because mmap is just so much more convenient. Okay, let's try this, run this again. Okay, so we were able to mmap 1 megabyte buffer size. Maybe we want to do our trick again here with the get character. I want to check out how this works. So get character here, here, and here. I want to see how this works. So what we do is we create a second window, and I want to check out htop here with SLP7. And let me just also share this window with you. Yeah. Now I have a problem that the window is too large. I have a second screen now, but the second screen is quite small. And yeah. Now it works. And now you can see all of this overlaid and no one can read anything anymore. Perfect. Let's maybe resize this a bit and move this maybe over here. Does this work? Oh yeah, this works, but you can't see me anymore, which depends on how you see it. Can be an advantage or not. Now you will be able to see me again. Okay. Okay. Now I'm in the middle of this htop. Maybe I should resize this a bit more. Okay, let's move this up here. We don't really care about the CPU cores for now, so let's just move this up here. So you should be able to see now the memory that it allocates. Okay. Okay, so this didn't work because I didn't compile it again. So now I compiled it again. And now you can see the virtual memory allocated here, and you can see that it's 2400. Is it bytes, kilobytes? Let's see. Now we allocate 1 megabyte more. Okay, so this is kilobytes already. 1 megabyte more. Now it's 3500. Now the next step is the mmap, and let's see whether the virtual memory allocated decreases again. Yes, now it's 2500 again. So this works exactly as expected. It gives us virtual memory. If this is just virtual memory, not our physical RAM, let's try whether this also works with 1 gigabyte here. Okay. Last time we saw that the limit of malloc was quite low, so we couldn't allocate very, very large areas with that. Let's try whether mmap can do that. Oh yeah, 1 gigabyte allocated, and it's gone again. And it doesn't even take any time, and it doesn't consume any memory. You can also see this. If you check out the memory consumption here, the memory consumption does not even change. So let's try this again. Allocating 1 gigabyte, nothing changes because this is just virtual memory. It does not really, it does not relate to actual memory that you have installed in your computer. It's basically just a reservation. Like, I would like to have this memory at some point, maybe, and then later on the processor or the operating system figures out, yeah, if they don't use it, then I can promise them as much as they like. So let's take this one step further. This is the gigabyte. Will it work for a terabyte? What do you think? Terabyte of memory. And this is a file mapping. I could map 1 terabyte file. Let's see whether this actually works. Okay. This didn't work. Oh, and now we got a segmentation fault. This didn't work. Interesting. So this did not work. So 1 terabyte apparently is too much. So let's figure out how much works. 512 gigabytes. No, it doesn't like that. So also here, the limit appears to be something, maybe, is it like, let's try 16 gigabytes. So I have a suspicion that this also does not work. Oh no, 16 gigabytes works. Interesting. So let's see. Oh, yeah, of course, 16 works. Let's try 64. Because I have just upgraded the memory in this system. So now I have a bit more memory. So I can even run Chrome now on this machine. So let's try this. Okay, 64 doesn't work, but if you take a look at it, then I would expect that 58 should work. And this is just the regular check. Does this exceed the total memory installed in the system for now? Okay. I would like to see after how many gigabytes mmap returns 0. So maybe let's write a loop here before we do any of this. I just want to quickly do something, check something before that. So we will copy our mmap call here. And I will show you a second flag now. Map private is fine. And I will also use a second flag now. This is map anonymous. Map anonymous says that I don't use a file. I have to pass -1 here. So this is not a file-backed mapping anymore. malloc internally falls back to mmap with map anonymous if you try to allocate a lot of memory. So let's try to do this, and we will run this in a for loop and allocate gigabytes of memory. Let's see, we start at 0, I smaller than, how much should we allocate? A full terabyte, many terabytes. And what I want to do is I want to print the number of bytes that we allocated. So what we do is we print, in this case it would be ZU. So this is a size T and it's unsigned size T. And we will print gigabytes allocated. Okay. And this is I times, basically I is the number of gigabytes that we allocated, because every loop iteration we allocate 1 gigabyte. So how far can we get? Can we get beyond 64 gigabytes if we try this? Let's try this. Oh, okay, this is interesting. So I can actually allocate many gigabytes. Okay. Let's take this a step further. So I don't know how many terabytes I will be able to allocate. So make this a bit larger. Okay. And here, if buffer equals, we should check what mmap returns if the buffer, yeah, we didn't check that. Let's check mmap first. Mmap, what does it return in an error case? Of course, if we don't check the error value, we will never know whether it works. Okay, on error, the value map failed, that is void pointer -1 is returned. Okay, so we can just check whether the return value is -1. Let's check this. If buffer is -1, then we will terminate the program, exit 0. Sounds good. And otherwise, we will print gigabytes allocated. So maybe this did not work at all. Of course, if this always returns null, yeah, then things won't work. But we can also add a get character here before we call exit, because I want to see in this htop window how much memory is actually allocated then. So let's try this. Whether there is this limit that we cannot allocate more memory than we have in our system. Oh yeah, it forbids the comparison, so we can also compare this to a character pointer -1. Sure. Exit was not declared. Oh yeah, what is exit? No, wrong exit. Meant 3 exit. Standard lib h. Okay, let's include this as well. you see I always use the man pages. I always forget how all these functions work, so I check them out in the man page and then, oh, interesting. And here you can now see that we allocated 127 terabytes of memory. And look at the memory utilization. It didn't even change. Huh. Interesting. Now we terminate it. Nothing changes. So we can allocate 127 terabytes of memory. Interesting. This raises a lot of questions. What happens if we go out of memory, for instance? So these error return values, they are only useful if in very weird corner cases. Like if you have a program that already has allocated 127 terabytes of memory, you will get -1 as a return value and not before. Interesting. So let's remove this again. We don't need this anymore. You can write this yourself if you want to. Let's remove this. We also don't need this anymore. So we have our program again. We can read from the buffer, and now I think we are good in time for the next step. And the next step is, I will reduce this a bit again because we don't actually need to map a gigabyte. A megabyte is enough. And now we have time to use shared memory. So what we do now is we will use shared memory, and we will, if we use this, then yeah, we could use this, but I want to try something else. Maybe we have a variable that we want to share across processes. There's a question. Let me check out the question. Yeah, there are already 4 questions in the Q&A. Thanks for pointing me to that. I will just hide the htop window again. Is mmap, let me also hide this window here. Is mmap faster than malloc? So malloc will use some sort of some list internally that can be used to find the right allocated block. mmap does not do that. Mmap it's difficult to say whether it's faster or not. I think it depends a bit on the situation. So there are cases where mallocing memory can be faster, and there are situations where mmapping memory can be faster. I would say, as a rule of thumb, if you want to allocate a huge amount of memory, and this amount of memory will stay the same for a long time, then mmap is better. But it's similar with malloc. If you want to allocate a large amount of memory, you can also do this with malloc, and it will have a similar performance. If you allocate a lot of memory and use realloc all the time to increase the buffer size, then you will lose performance. But if you only do a single malloc to allocate memory or a single mmap, there won't be much of a difference. Why did it work to allocate 127 terabytes with for loop, but not with increasing buffer size? Because there is a very, very stupid check in the operating system that says if a user tries to allocate at once more memory than we have in the system, then we return an error code. You can work around that with some additional flags, with some additional configurations. You can disable this in the Linux kernel configuration. But the other option is to just use multiple allocations. Doesn't malloc call mmap after 1 megabyte? Yes, you have correctly observed that malloc falls back to mmap. A question at the beginning, with which command can I determine the binary size? The binary size, the program binary, well, let's maybe try this. Okay, so let's try ls. We can see the binaries here. And I use the Z shell. You will find the commands to install the Z shell and this config for the Z shell on the website. So there I have a command LA, which is a shortcut for ls-LA, more or less. And there you can see, for instance, the file size. You can see the file size. The CPP file is 378 bytes. The binary size here is 16,944 bytes. Okay, so this is basically answered. Let me hide the window again. Could you please explain kernel page fault and code page fault? It appears in A3 and I don't know what they actually could be. Yeah, tricky. I don't want to go into much specifics here. We cover in the lecture everything that you need to know. And in A3, the specific answers, I cannot provide you information to the specific answer options on whether they make sense or not. The thing is, the correct answer might be clear even if you have other answers where you are unsure what they even mean. What are the advantages of using the POSIX IO instead of the CIO functions? One advantage, we have just seen that, is that we can use mmap together with them. Why can't we allocate more than 58 gigabytes with mmap at once? The limit is determined by the amount of physical memory that you have installed in your system, and I just upgraded to 64 gigabytes in my system, so 58 gigabytes were free available RAM. And there's a simple check in the operating system that says, please do not allow an mmap or a malloc allocation with more memory than the system has at once. But if you have multiple allocations, then it's fine. Then I don't care. Okay. Virtual memory equals heap, stack, BSS, etc. Or am I wrong? Virtual memory. We always work on virtual memory. We can see how much physical memory is in use. You can see that with, for instance, with htop. You can see the physical memory in use. You can see that up here. But from a process perspective, we only care about virtual memory. There's no way to directly interact with the physical memory. And this is also what is important. And in this lecture, maybe in this lecture, the most relevant part to learn about this memory mapping things. We work in virtual memory. We don't care about the actual physical memory. We need to know how virtual memory works so that we can write efficient user programs, but we don't care how this is implemented. Not as user space programmers. At what point will we get the results to the questions in A3? After the deadline or after all the question hour slots? After all the question hour slots. So the letter is correct. You can see Daniel getting hyped up when saying shared memory. Okay, interesting. I didn't notice. But, oh, another question. But I thought that you can allocate with malloc many gigabytes, but as soon as you use it in form of accessing data or writing it to then the kernel doesn't allow it. At least at malloc it does it like that. It's the same for mmap. It's the same if you allocate. We've just seen that if you allocate gigabyte wise, blocks gigabyte wise, then you can also allocate. Here you've seen that before, 127 terabytes of memory, and it doesn't fail until then. And you can try to write to these 127 terabytes of memory, and of course then something will go wrong, and the kernel then will at some point say can't do it. But Before that, the kernel first says, yeah, that's fine. When you were calling mmap in a loop, were you creating memory leaks, or did the allocations add up into one mapping? No, this was creating leaks. Yeah, I was creating a lot of memory leaks there. Sure. What if I cannot answer all the questions in A3? Meaning there are questions which have no correct answer. There are questions which have no, or I'm not entirely sure, but I think there are questions which have no correct answer. Why is the 127 terabyte limit there? The 127 terabyte limit, this is a part that we cover more in operating systems. This is due to the way that current processors are implemented. But this will change in the next years. So maybe in 5 years from now, you will have a computer which doesn't have the limit of 127 terabytes, or if more likely this would, the actual limit would be 128 terabytes, but there are also other allocations in our program already. So 128 terabytes, and this will change to 64 petabytes within the next 5 years for many computers. This is just a specific implementation detail of the processor, why this is 127 terabytes. But you can expect the same limit here on Intel, on AMD, even on 64-bit ARM processors, you would observe a similar limit. Does mmap store data on the stack? The pointer that you get returned from mmap, this will be 8 bytes. The pointer will have 8 bytes, and this pointer will be stored on the stack. Other than that, mmap itself does not store any data on the stack, no. Okay, I would say let's continue a bit with the coding part. So we will implement a bit more. And for that, we will go back to the code. Let's check out the code. So we wanted to create shared memory, and for that we will use fork. We've already used fork, we have seen that, and now we will change this map private. We've already read that. We can use map shared here, map shared. And now both processes should be able to run the printf, but also both processes need to unmap it, right? Both processes are running here now. Maybe we want to distinguish between parent and child. So maybe we want to store the PID here. PID, if PID equals 0, then this is the parent process. And I see there was one more question in the YouTube chat. I can of course answer this as well. If virtual memory is where malloc and mmap initially reserve memory, then what is reserved memory? The reserved memory column in your htop window. Yeah, the naming there is not very fortunate. I usually stick to the terms virtual memory and physical memory because they are very clear. If you take a look at htop, virtual memory is virtual memory, and this would be the memory, the physical memory that is used by this process, but not all of the memory. And I'm also not entirely sure. I don't think it's the exclusive memory here. But there's also another column. If you would go a bit to the, let me go a bit to the right. The shared memory. This is also memory that is allocated to this process, and I find it a bit unfortunate that operating systems do not always make clear in which cases physical memory is actually consumed. What you usually can assume is that the overall memory consumption that is shown for the process, for instance, this will be more related to the physical memory of the system. Also the memory up here, you can see this is 62.6 gigabytes. This relates to the physical memory installed in the system, so you can be sure that if this fills up, this refers to the physical memory. The reasons why this is that the operating system has a lot of optimizations that make it less clear to which process memory should be counted. It can be counted to multiple processes. Maybe there's also a lot of memory that cannot be counted to any process because it currently is not used by any process that is running. So we will have parent and child here again. I will just duplicate this code to have some behavior difference in the printf. I want to have a different printf. So the parent knows the child, so the parent is here, and the child doesn't know the parent, and so the child is here. Okay, that makes sense. Fork, PID 0, printf in the parent, unmap in both. We used map shared. Let's try whether this works. G++, and we run this, and oh yeah, parent and child both can use this. And now I want to try something. So I want to do the following. So first I let the child sleep 1 second and let the parent print. And I will let the parent change the first element of the buffer into X. And then the child will print this. Let's see whether this works. Oh, it doesn't. Oh, it does? Oh, yes, it did. But of course, the process terminated very quickly. So maybe let's add another sleep here so that things look less confusing. Or we could use await PID. Actually, wait PID would be much nicer. Let's use wait PID. We wait for this PID with default values. Let's try whether this works. Wait PID was not declared. Let's check out what wait PID requires. We don't want the status. We don't care about the options, but we care about the includes. A lot of includes already for that small program. Okay. And then we are here. We can now compile this again. Yeah. So okay, this is not really great because we can't recognize whether this works. So maybe we will say ++ or yeah, we do the following. We want to have this iterate through the alphabet characters. So we base this to A. Okay. Every time we run this will go to the next letter. Modulo 26, because 26 letters in the alphabet. And then +A again, because we want to have this start with large letter A. Okay, so let's try this. We run this. Yeah, this does not really work. Buffer equals buffer plus, oh yeah, we need to, of course, +1. We need to increase the number by 1. And if we run this, perfect. So this is working. This is working. Bello world, also fine. And you can also see, because this is map shared, right? This is map shared, and it said with map shared, the changes are written back into the file. Oh yeah, they are now in the file. So this is a persistent change that we made now. So we can change the file, and parent and child share this memory, and they can interact on this memory. Okay, if they can interact on this memory, they can. I'm sure they can also do something more interesting here. Okay, I will do something very ugly now. I will use busy waits to synchronize these programs. While buffer 0, and now I will use the same logic here. Or actually, I don't. I mean, this doesn't have to be a printable character. While buffer 0 modulo 2 equals 0, we wait. We just want this process to wait. Okay. Printf child changed a value to, and then we print a character, buffer 0. Okay. And now we need a while loop here again, while 1, so that we can really see that they can interact in both directions. Okay, so this runs forever, while buffer 0. Okay, maybe forever is a long time, but that's fine, that's fine. It should be fine. Let's copy this. We will do the same code here. We can actually copy the entire code. 8 lines, something like this. So, okay, and now this is the parent. Parent changed value to this. And now we check if it's not 0. So the parent will always change the value to the from odd numbers to even numbers, and the child will always change the values from even numbers to odd numbers. And let's add sleep 1 here for now, so that we can also see what is happening. And this is also not properly synchronized. We would need mutexes or semaphores here to synchronize this properly. Oh yeah, this seems to work. Okay, really nice. So let's try this with usleep, and then maybe 1000, that would be a microsecond. Maybe, yeah, let's try 10 per second. That would be 100 milliseconds. Yeah, usleep is microseconds, so it is then milliseconds, 100 milliseconds. Okay, let's try this. Oh yeah, very nice. And now this iterates through all the letters and continues, and you can see that this just works. Sometimes the printing is in the wrong order, but the letters are all there. But of course, this is not properly synchronized, so you probably will see cases where letters are duplicated and things like that. The thing that I want to now look at is, because this is working with a file, what if we don't use a file? Okay, we can still do that. We can use map anonymous. We have seen map anonymous. Map shared, -1, because we now don't need this content from the file anymore. We are writing there anyway. Okay, let's try this. Ah, yeah, okay, so this starts at a very weird offset, right? If we scroll up, it's still printing. So it starts at a very weird offset. So this is a bit odd because the memory is not initialized, right? We would have to initialize the buffer because otherwise we are using uninitialized data and we never know what this data will be. Buffer 0 equals A. Then it's initialized. Ah, yeah, now it starts printing at B. So this is good. Map anonymous. But what if we don't want to use map anonymous, and if we want to start these two programs independently? Let's do this. So I will copy this now. I will copy SLP7 CPP into SLP7 parent CPP and into SLP7 child CPP. And we will take a look at these. Let's take a look at the child first. It's this part here. We don't need the fork anymore. We don't need the wait PID and unmap anymore because we are not terminating this program anyway. And we should, of course, take care that we are cleaning up everything. But in this example, if I have a while one loop, I don't have a meaningful way to terminate this. A nice way to terminate this program is to add signal handling. For instance, if you press Ctrl+C to exit this while loop, and then you can clean up everything. If you press Ctrl+C or Ctrl+D, that would be one option to terminate the program like that in a more beautiful way. Now we will not use map anonymous anymore, but we want to map a shared memory file descriptor. So we need a file descriptor, and yeah, something needs to be filled in here. Okay, so this is the child. Let's actually copy just this to the parent. Okay, and let's edit the parent also, SLP7 parent. I think we have a good timing here. Okay. So let's see. We have the child here. We have parent changed value, map shared, and we need to fill in what the FD is. Okay. And for this, we will use a new function, and this is called shmopen. shmopen. Oh, okay. We have another header to include. Let's check whether we already included it. Oh, we already included this. So we already have this. shmopen. We need to link this with LRT. So when we compile this, we shouldn't forget to pass -LRT. And this is the function we want to use, shmopen. shmopen creates and opens a new or opens an existing POSIX shared memory object. This is not a file. Even if this has a path, right? This will have a path, a name. It's not a file. It's just a handle which can be used by unrelated processes to mmap the same region of shared memory. Okay, so shmopen. A shared memory object should be identified by a name of the form /some_name. Okay, that is a null terminated string, and it has to have an initial slash followed by one or more characters, none of which are slashes. It will even work if you don't do that, but this is just for portable use. Okay. Flags, we also have flags here. We have the name, we have flags, O flag and mode. The O flag is, oh, this is similar to the open flags that we already know from the open call. So, okay, this is easy. We know this already. And what about the mode? Where was the mode? Mode. Yeah, if we create this object, we might have to provide some bits here. And this is the same bits that you know from the terminal. But there are also POSIX equivalents, and I will show that to you in a second. So we need to use shmopen. We provide a path here, and this is just, I will write this in a non-portable way because I don't care about it for this example. My shared mem. And oh, now I forgot what the other options were. Very bad memory. O flag and mode. Okay, so let's check out the O flags. This should be basically O read write because we want to read and write. And then the mode flag, we need to provide some file access permissions basically there. And what you usually want to do is here you can provide something like 0644 or something, or 666 or 777, whatever you like, whatever permissions you want. These are the Unix permissions, or you can stick to the POSIX variant of defining them. So these are basically the constants that you OR together. We can also try that maybe just to illustrate that. Return 0, and we will just printf these. Let's try it like, yeah, let's try it like this. I will print two numbers here. The one is this one, and the other is yeah, now we have to know what exactly the modes are. 600, maybe this is the the same mode. Let's try whether this works. G++, SLP7 parent. We want to compile this into SLP7 parent, and we want to provide, we shouldn't forget that LRT, because we want to link this with the mmap and shmopen functions. Okay, that ZU, it doesn't like it because the argument is an integer, of course. Integer. Let's try what this yields. Yeah. And we will now execute this SLP parent. Ah, yeah. So this is the same permission. It's the same number. So instead of providing this that we know from file listings, right? If we look at LA again, you can see this here. This is 6 and 0, and we have 0 here. Here we have 7, 7, and this would be is this 5? I think this is 5. Here we have 6, 6, 4. Here we have 7, 7, 7, 7. Yeah. Okay. So we can use either of these options to specify the permissions for this shared memory. Now I think I will need a second window again. And for that, I will use the htop window that we've already had before. I know it's a bit small, but I will only use it to start the parent process. So this will run up here. Okay. And I will use this to run SLP7 parent. Yeah, I need to compile this first, of course. Let me compile this. Okay. And now I will run this. I get a segmentation fault. This is not nice. Oh, I should open the editor in this window here. So why do we get a segmentation fault? Let's check out the man page of shmopen. Something, we must have forgotten something. shmopen. Okay. Okay, let's see. Oh yeah, here. Upon successful completion, shmopen returns a new file descriptor referring to the shared memory object. The file descriptor is guaranteed to be the lowest numbered. Okay. Normally used in subsequent calls to ftruncate. Oh, and mmap. Yeah, we do this part. We don't do this part. Let's check out ftruncate. Man ftruncate. Ah, yeah. Okay, we need new includes for this. And truncate, what does it do? The truncate and ftruncate functions cause the regular file named by path or referenced by fd to be truncated to a size of precisely length bytes. Okay. Okay, so we can basically determine the size of the shared memory object with that. We need to include this. We already have types included, so this is fine. So what we need to add is here ftruncate on this file descriptor, and we want to make it buffer sized. Buffer size should be the size of this shared object. What am I doing? Before we had shared memory between the two processes, but this was based on a file. What we do now is we want to start the two processes independently and still have shared memory. We don't have fork anymore. So they now need to have some handle that they can use to refer to the same shared memory. This is what we're doing. This handle will be my shared mem in this case. They will both open this handle, this shared memory object, and then mmap this with mmap, and then work on this shared memory. To create this shared memory file descriptor and make it usable, we have to define the size of this shared memory object, and we do this with ftruncate. Ftruncate defines the size of the shared memory object. File descriptor, and then the buffer size here. Ftruncate, buffer size. Let's try whether this works. So we again compile this and we run this. I will run this again in the other window so that I can work on the child then subsequently. It's still seg faults. Why does this still seg fault? Let's check out why this still seg faults. And to do that, we will use a debugger maybe. Yeah, let's use a debugger -g. We will run this with gdb and then slp7 parent layout source. We want to see the source. We want to break in the main CPP or in the main function. Yeah, run. Okay, now we are here. We want to step one step and we want to print fd. Fd is, oh, this is not good. So it's 32,000. Doesn't sound like a good value. Let's go one step further. Okay, next. Now it's okay. It wasn't initialized. Oh, fd is -1 now. -1. So this did not work. We were not able to create this shared memory object. So this is the problem here. We cannot create this shared memory object. Let's try this with a different name. Let's try this with /my_sharedmem. And I will do something here to speed this up a bit. If fd is -1, exit -1. And now I can run this and, oh yeah, still -1. Where do I have to put this shared memory? Let's check out shm open again. Okay, /sumname, I did that. Oh, I need to, this file doesn't exist. create. Of course, I forgot create. Yeah, we mentioned it before that we need this, but I forgot this entirely. So let's use create. Otherwise, we wouldn't need these flags back here anyway. They were just a description for create. So let's go back. Always a good idea to check out the man pages first and not skip any part. Oh, now it works. Okay, so this is great. This works. So we will now run this here. And now we just need to fix the child process and do the same things there. So let's also open the child process. Okay, so we have this here. We don't need create here because we assume that the parent is already running. So we also don't need any permissions here because we don't create this file. We also don't, do we need ftruncate? Yeah, we need ftruncate because otherwise it will not know the size. Actually it might be because the parent already used ftruncate. I think we don't need this anymore. So let's try not compiling the parent again, but compiling the child. And now we will run slp7 child and nothing happens. Wow. This is a bit underwhelming. I was expecting something to happen. Yeah. So maybe let's printf the value of buffer here so that we know what everyone is seeing. Sees C. And we also want to have the same in the parent. And I hope I can figure out what the bug is before we run out of time. Parent sees this, okay. Let's terminate the parent. Let's compile the parent and run the parent again. Okay. Okay, so parent sees A all the time. We compile the child, we run the child. You also saw that it's no problem to run multiple parents at once. Also interesting. Let's edit the child again. So the child sees A, but it doesn't do anything. Oh yeah, because my logic is flawed. The logic is flawed because both are checking if this is 0 because I copied this into the other process. So let's see. Yeah, now it works. Perfect. So we can see here now that this works as expected. Okay, yeah, maybe let's leave the microphone where it was for now, and move instead the window somewhere else, because yeah, maybe like this. Okay, so we can see parent and child are interacting, and as soon as one of them stops, we can also stop them. Yeah, very nice. With Control Z, you can pause a process, move it to the background. Yeah, this works. So let's check out what the chat has to say. Okay, so the chat says, so in order for this to work, a file is being created. No, this is not a file. This is working entirely in memory. It is, you could call it a virtual file, or yeah, it's basically, it exists in the Linux file system, but it does not exist in terms of a file on the disk. This is not on the disk. This is very important. It's not on the disk. In contrast to the memory mapped file that we had before. I will now terminate this and also this other window, okay? And maybe hide one of them so that we can move to the, or hide both of them and move to the last question for the day. So let's continue with the next question. And this is about mmap. Question 2 of 2. Make sure that you're still there. And we start the quiz in a few seconds. And the cat, I don't think the cat is here. No, the cat is not here. Nope, nowhere near. So the cat is not here. Let's start the quiz. mmap. Oh, this should be mmap. It's cut off on the slides here, but it says mmap on your phone. Can provide access to the memory of another process. Cannot create shared memory between processes. Shared smap. Can map files into memory for more convenient access. Can only create small memory mappings. Yes, this is also what I would say is the correct answer. What mmap cannot do, and this is why I phrased it this way, mmap cannot provide you access to the memory of another process without the other process defining, I want to share, I want to have access to this shared memory. So it's not that you can get access to the memory of another process, but you just get access to a shared memory region, and the other process also gets access to that shared memory region. So they both get access to a shared memory region. That doesn't mean that you can mmap, for instance, the stack from another process into your process, or the heap, or the data segment, or the code. This is, I would not say that it's impossible to do this with mmap, but this is certainly not what mmap is built for. So of course, if you are more close to operating system development, then maybe you can do some things in that direction. But in general, I would say it's not correct. You cannot you cannot use mmap to directly gain access to the memory of another process. You can share memory. You can definitely create shared memory between processes. smap is something entirely different. I just tried to come up with some logical explanation why this would make sense. Can only create small memory mappings. We've seen that 60 or 58 gigabytes was possible. So definitely it can create large memory mappings. It can only map, it can map files into memory for more convenient access. Yes, we've seen that today in a lecture, so this is correct. And with that, we get to the leaderboard, and let's see who got the most points today. And this is 292. And yeah, congratulations for the bonus points that you just gained. Yeah, bit of applause here, of course. And with that, we get to the Q&A, which is the last part of today. I already answered this. I checked where the cat is. The cat was nowhere near, unfortunately. Sorry, but why did we transition from open to SHM open? Open opens a file that exists on the disk. SHM open opens a file descriptor that does not exist on the disk. It just exists in memory. So the advantage is that we are now creating shared memory that is just in memory. We are not using shared access to a shared file. The previous example was also shared memory, but it went more or less through a file, which will also still remain in memory most of the time, but it's still a file. It's on the disk. What is the difference between address space and virtual memory? For a user space programmer, virtual memory, address space, that's basically the same. For a user space programmer, you would say the address space, or you could say the virtual address space. You don't care about the physical memory so far. But as soon as you care about the physical memory, but this is something for next semester, not this semester, then you will also talk about physical memory and the physical address space. But for now, we just talk about the virtual address space and virtual memory. So mmap allocates on the heap as well. No, the heap is organized. The heap is a data structure that you actually will implement in SLP. This is one of your assignments. And you will implement this, and then you will see how the heap actually works. It does not allocate memory on the heap. But the other way around, if malloc says this requested memory that the user requested is too much for the heap, then malloc will fall back to mmap and use mmap instead. Does each process get its own virtual memory, or does it share it? I think you might have seen that, for instance, if you have global variables in two processes, you start the same process twice, same global variable, same address, you printed the address, and you modify the variable in both processes. You have seen that they don't interfere with each other. They don't share it. So they must have separate memory. They must have separate address spaces, separate virtual memory. Could you briefly explain file descriptor again? So a file descriptor is just a number. If you want to access a file, the operating system has to do that because the operating system keeps track of all the files. It organizes the file system. So the operating system, you will ask the operating system to open a file, and the operating system opens the file, but it doesn't give you the file back itself. It only gives you an identifier, a number, pretty much as if you go out and you leave your jacket at the reception. At the Garderobe, then you will get a number, and with this number, if you go there again, they will be able to find your jacket again. And this is pretty much the same here. The operating system just hands you a number, and with this number, the operating system will be able to find this file again. So the file descriptor is nothing but a number. Where in the memory are shared variables located? Good question. I think this question is also part of A3. You can try this. You can just create shared memory objects and look at the addresses, and you will see where they are located, in which range. We've already heard a few times whether shared memory is allocated on the stack. It's not allocated on the stack. Take a look at the addresses, and even if you see the addresses, it's not allocated on the stack. How are virtual addresses stored? Virtual addresses, a different word for that would be pointer. A pointer is a virtual address. Pointer, how do you store a pointer? in a local variable, for instance, a pointer variable. And this pointer variable would basically store the address. Yeah. Could you specify one of the answers in the questionnaire? When my system runs out of memory. When my system runs out of memory, I would assume that I mean the system runs out of memory. Not my program runs out of addresses or anything like that, but the system runs out of memory. There's no more RAM available. Does that specify the question enough? If not, just ask it again. Could you give a brief overview on how SHM works in the background? In the background, so you ask the operating system with SHM open, please give me a shared memory object. The operating system internally creates this shared memory object and just gives you a number to identify this shared memory object. You use ftruncate to tell the operating system the size of the shared memory object, and then you have a shared memory object of a certain size, and then you can write into this. You can, well, first of all, you have to mmap it, and if you mmap it, the operating system will, depending on what you mmap and how you mmap it, just give you empty pages, and these empty pages you can fill them with data. And whenever another process tries to mmap the same SHM open first and then mmap the same pages, it will give these other process the same pages, access to exactly the same memory. And that is why when you write to these memory locations, the other process immediately sees this. You will implement this actually in operating systems next semester. So it makes a lot of sense to use this from a user perspective first, because before you have to implement it next semester. And then you will also learn how this works in the background in all detail, because you will implement it. Are shared memory variables just variables allocated with mmap, or do I have to make a new process in order that is shared memory? It depends on the flags. It depends on the flags. So we first used mmap today to create local process memory that was not shared memory, and then we used different flags, and then it was shared memory. So you have to pass the right flags, and then it would be shared memory regardless of whether there's a second process using the shared memory, but it would be shared memory if you pass the right flags. How would we lock shared memory? We would need to, for avoiding conflicts, right? Yes, yes, of course. So the shared memory, for instance, I use the character pointer here, but imagine using a struct pointer instead. You define a struct, and a member of the struct could be a semT or a pthread mutex t or a pthread cont t. And then you can use seminit or pthread mutex init on this semaphore or this mutex that is placed in a struct in shared memory. And then the other processes can also access the same semaphore or mutex with the regular semWait function or the mutex log function. You just have to take care that in the seminit or mutex init, you have to pass the right values, or in case of mutex, the right attributes, so that the log will be shared across processes, so that the log knows that it's placed in shared memory. But then you can use this in multiple processes. We could have waited a bit to start the question. I was late because the page had to refresh. I'm very sorry about that. It's always a bit of a challenge. So I waited a bit, but I could have waited longer. Sure. Yeah. Sorry about that. When I malloc 100 kilobytes, I get a really low address. When I malloc 200 kilobytes, I get a really high address, much nearer to the stack. Second is higher than program break. What gives? So what is the reason for this? There are tools that you can use to check which system calls a program uses, strace. You can use this to check which system calls your program internally uses. And you can also use a debugger to check which functions in user space are internally called when executing this program. I would suspect that for the first program, this is really allocated on the heap. And for the second, with 200 kilobytes, this will take a different path. Maybe just take a debugger, step through this, and check whether you see a function call that you already know from today. And then this might be the reason for the different addresses. Is operating systems even possible besides other lectures in terms of difficulty and time consumption to pass it for an average student? Because it seems really hard how you describe it. No, it's of course, operating systems is not an easy course, but I don't think it's true that you can't do any other lectures besides operating systems. I think for the average student will do the regular 30 ECTS in this semester. This is not uncommon. So I also see this range. Of course, ECTS, the amount of time that you have to invest will be different for every student. ECTS is an average number. And you will observe that for different classes, different students will take a different amount of time. There will be students that take very small amount of time, for instance, for math lectures, whereas the same student might take more time, for instance, for programming intensive classes. There might be students that take less time if it's more related to something like visualization of data than if it's related to system level implementations. And you will see a different curve for all of these lectures. So you will have some distribution, and every student for every lecture will be placed somewhere else on this curve. So of course there are students for operating systems that are very far on each side, especially if you struggle with C and C++. If you already have a problem debugging regular user programs, this will be very time intense because you will need to debug. So yes, it will be time intense. On the other side, we see students that take very little time because they are used to debugging already a lot, and they also are used to programming in C, C++ a lot, and then they also introduce fewer bugs, and then it takes less time. It also depends a bit on the team. If you have team members that also are on a very good level, and you are also on a very good level, the time that you have to invest will be much lower. It goes very far to both of the sides. So there are students that say, I couldn't do anything besides OS in this semester. And I've also seen every semester we see student groups that say, from our group, each of the students did not invest more than 50 hours into this class. And this is a 7 ECTS lecture, so 50 hours would be for an average student 2 ECTS. But this is not how ECTS work. You can't directly translate 50 hours back to ECTS, because this is an average. ECTS does say exactly that you have this curve, and there will be some that only take 50 hours, and there will be some that take substantially more time. This is exactly what the definition says. What can I say more about this? I know many students that were more on this side, that took really little time. The bad part is always if you figure it out too late that you need more time. So getting things done early is better to be on the safe side. So time consumption to pass it for an average student. If you look at the statistics from operating systems, I would definitely recommend always to look at old evaluations and statistics from different classes, because this tells you a lot about the class. And you will see that in operating systems, yes, there are many complaints that it's a lot of time investment. And we are constantly trying to bring this down by improving the debugging possibilities in this operating system, in this educational operating system. And we already have seen that this significantly brought down the time investment required from the average student. But of course, this is a process that will still continue and will always continue. If we stop trying to improve things, things will get worse. So we always have to try to improve things. But if you look at the statistics, the grades, the statistics there, you will see that only like 30% of the students fail the class, and about 30 to 40% get a 1 in operating systems. It's still a lot of time investment, because what we do in operating systems is we give a lot of bonus points. There is basically no limit for bonus points. And many students really start enjoying this topic and start working more and more on this, because it's also rewarded, because you get bonus points for everything. And even if you then have only very few points on the test, you will still get 1. And this is the effect that we observe there. We have 30 to 40% of the students get a 1 because they invested so much time into bonus tasks, which they wouldn't have to do. So if you look at the point distribution in operating systems, you will see that the average number of points on the exercises is close to 90 out of 100. So the average number of points that the groups achieve is much higher than it would have to be, because ECTS says, well, there should be 5% 1, then maybe 10% 2s, and so on. But this is not the case here, because we allow students to invest more because they are interested in it. Of course, if we would say this is not allowed, then students would stop investing time into this. But I don't think this is very helpful. If someone is interested in a topic, we should, of course, support this person in their interests. And then we end up with student groups that have on the one side up to 200, 150 to 200 points out of 100 that should be reached, including both practicals. And then this is already beyond the grading scheme. So this is also for the overall grade far beyond a 1. So they invested way more time than they would have to, because it was interesting. And I hope to keep operating systems as interesting as possible. And therefore, I'm not sure how far I can bring this down, the time investment from the students there. But I will definitely try to improve and reduce the time consumption for the average student that does not want to invest more time into this. So is virtual memory even relevant for malloc in terms of denying allocation? A very good question. Very good question. You asked the right questions. I'm not answering it here, but it's a good question for that you might want to answer in the design discussion. Where does mmap allocate memory? In the address space, somewhere in the address space. Can the top 5 people get a bonus point, please? Did we say top 5 points? Top 5 people get a bonus point? I don't recall what we said in the first lecture. So maybe yes. I will check it after the lecture. One of the questions asks if malloc will fail if there is no coherent space in virtual memory. Virtual memory is much too big for this to happen in practice. How should we even test this? I think I've showed you today how you could test this with mmap. Why don't you try the same with malloc? Can we continue with A3 after the deadline tomorrow? There's no coin usage and the discussion round is next week. I think the deadline ends with the possibility to answer A3 questions ends with the deadline tomorrow. I don't think there is any possibility to use coins to hand in the answers later, to answer the question later. So the deadline for A3 is without an extension, unfortunately. But you can answer it, and you can still get points. You can get more points than you get from the questionnaire through the discussion round. So is flag map shared? Is it shared memory? Yes. And with that, we are almost done. Favorite book. Favorite book. I must say I'm not a big reader. I do like reading technical material. So I enjoy reading. So I don't enjoy reading novels or anything like that. So if I read something, it's something technical and usually something that is for work. But there are many documents, many papers, books even that I consult a lot for work. But of course, it's different than a novel. So I don't have a good answer for this. Do you contribute to the Linux kernel development? So in 2017, we designed a security feature that we called the Kaiser patch, and this has been integrated into the Linux kernel. From this patch, I might have 1 or 2 or 3 lines of code that are from me. There's a much more significant part of code that was written by Richard Fellner, who was a operating system student in if I'm not completely wrong, I think it was in 2015, and he was then a tutor in 2016 and 17, I think. And then he wrote this patch for the Linux kernel as a master's thesis. And we submitted this to the Linux kernel mailing list, and then it was merged in the second half of 2017 into the Linux kernel. So so in that sense, we contributed to the Linux kernel development, but only if it's related to our research. Also, there are a bunch of further vulnerabilities that we have worked on that led to Linux kernel patches, and I think this will continue like that. So I would expect more Linux patches in response to the research that we do, but also in other operating systems. Did you have contact then to Linus Torvalds? Yes, I emailed Linus Torvalds on a few occasions, and I was surprised that he answered the emails that I sent to him in most cases within a few minutes. So this was really nice. And my experience with him, I know that many people had a bad experience in the communication with him. I didn't have this experience, I know that he has been working on his social skills there, but this was actually before that time, even before he took the time out there. I think working on social skills is a good thing for everyone. Also, I'm constantly trying to improve my social skills, and if we stop doing that, we will get worse. It's the same as everywhere. If we stop trying to improve, we will get worse. But on a technical level, I had contact with Linus Torvalds, and the communication there was good. Will there be any CS nights in the near future? Given that we have lockdown again, I think basically going out on the weekend doesn't really work anymore. I think it would be really good for socializing to establish more of these game nights, not just CS, but basically any computer game that you want to play. And we have this category in our Discord server. So if you want, just make a poll and ask whether we should organize another game night on specific date. And if you get a lot of thumbs up, we will just make this another game night. Sure. Did you read Harry Potter? I've watched the movies many times. I've listened to the audiobooks also. I didn't read them, but I heard the audiobooks. So I think I know the content from the books, but I didn't read it myself. I find reading, I'm a very bad and slow reader. I'm trying to improve that, but it takes time. Therefore it's not very enjoyable if I read text and then I'm basically as slow as the audiobook, so I can't read faster, and then I can also just listen to the audiobook. When talking about the location of static or global variables in A3, are you referring to initialized variables or uninitialized? Does it make a difference? If it does a difference, I would assume that in terms of the question, you should look at a consistent way. So you shouldn't say, okay, there are 4 different variable types. Let's say global, static, heap, and stack. And I will look at global initialized, static uninitialized, heap, and stack. This wouldn't be a fair comparison. So if you would compare them, then please make global and static and stack and heap as far as possible all uninitialized or all initialized, just to have a fair comparison. Because otherwise, you are measuring whether initialized or uninitialized makes a difference, and not whether any of the variable types makes a difference. So this is just a thing for consistency. Next, Master sees is finally installing Linux as convenient as Windows. Actually, I must say, installing Ubuntu on a clean machine today is just as convenient as Windows. You plug in the USB stick, it boots, you click install, it's installed, done. So this is actually working out of the box. I didn't have any problems with that anymore since several years, actually. On the other side, with Windows, so on Linux, you now have often the situation that everything works out of the box unless you have very exotic hardware, maybe. But for Windows, then you have Windows installed, and then nothing works because you first need the Wi-Fi drivers and everything else, and all the drivers need to be downloaded and installed, and you can't do this without Wi-Fi at first. So I actually find this more inconvenient than Linux today, because Linux often can do this because it comes with more Wi-Fi drivers. Okay, with that we answered all the questions, and I would like to thank you for being here, and with that close the lecture for today. So thanks for being here, and see you in the question hour in a minute.